Dear students, welcome to this new class. In the last class, we discussed the basic properties of a isomorphism and proved some results related to the isomorphism. In this class, we try to prove the isomorphism theorems. First, we try to one results related to the isomorphism, and then we move to the isomorphism theorem. So let G be a cyclic group of order n, then G is isomorphic to Zn. And if G is an infinite cyclic group, then G is isomorphic to Z. So these are the two important results. We have to just say that whenever we have a G is a cyclic group of order n, then G is isomorphic to Zn. If G is an infinite cyclic group, and then we can say that we have a G is isomorphic to Z. Okay, so let's start with the first one. We have to suppose we have a given G is a cyclic, so we have a suppose G is generated by A, and now we have to show that is isomorphic. Then isomorphic means there exists one map which is bijective homomorphism, and then because G is isomorphic G2, we have to proving that G is isomorphic to Zn. So this means we have to define a map phi from G to Zn, and then because the element of a G is nothing but is equal to G is a cyclic. So if it is cyclic, then G is generated by a element A, and if it is generated by A, then we have to define phi of a to the power k, and now the element of Zn is nothing but is equal to, you have a equivalence classes are there. So we just say that we define a phi a to the power k is equal to equivalence class of a k, where this k is lies between 0 to n. So we have to define this map. So first objective is this map is should be well defined, and then we try to show that this is a 1,1 onto and homomorphism. So that means we can say that if satisfy this map, satisfy all the properties of this, then we can say that G is isomorphic to Zn. So for well definedness, we have to take two elements a to the power k is equal to a to the power m. And now a to the power k is generated by this, then we can take if a to the power m is the element of a G, then a to the power minus m is also the element of a G by the inverse property, because G is a cyclic group. So if this we can just a to the power k into a to the power minus m is equal to a to the power m into a to the power minus m, then a to the power k minus m is equal to, you have a identity. So we can say that a to the power k minus m is equal to identity. Now this result is saying that if a to the power minus k is equal to identity, then because G is a finite group of a order n, that means n should divides the this k minus m. So n should divides k minus m, and if n divides the k minus m means by the congruent modulo property, then k is congruent to mod m mod of n, and if k congruent to mod of m, then we can say that equivalence class of a k and the equivalence class of a m are the same. So this means we can say that this means k minus m is congruent to 0 mod m, or k is congruent to mod m, then that means the map is defined this phi a to the power k is equal to equivalence class of a k is a well defined. So this means the first thing is the V phi is a well defined. So we have to prove that this phi is a well defined. Now next we have to try to show that this is a 1,1. For a 1,1 we take a phi of a to the power k is the same as a phi of a to the power m, and then by the definition this can be written as a equivalence class of k is the same as the equivalence class of a m, and now equivalence class of a k is the same of m, and then you have a order of a G is equal to n, then n should divide the k minus m. This is equal to, you have to take a mod of n, and then if n should divide the k minus m means you have a this k minus m is equal to some nq, for q is the element of a z, and now if k minus m is equal to nq. Now we write a to the power k minus m. So a to the power k minus m is equal to a to the power nq, and now n to the power q. And now because we have a this group is the order of a this is equal to g, and the order of a g is equal to n. So a to the power n is equal to, you have identity, then you have identity, and then e to the power q is again you have identity. So ultimately what we getting this a to the power k minus m is equal to identity. Now this group is a cyclic group generated by a. So this is all the elements of this a to the power some powers of this. So this is a to the power k into a to the power minus m is equal to identity. We can write a to the power k, a to the power minus m into a to the power m is equal to e into a to the power m, and now we have to a to the power k is equal to, this is identity, and then is equal to, you have a to the power m. So we show that ultimately if we have a phi of a to the power k is equal to phi of a to the power m, then we show that a to the power k is the same as a to the power m. So we prove this clearly. This phi is a 1 1. Now we try to show that phi is onto. For onto, that means we have to x is the element of an Zn, and if x is the element of a Zn, then x can be written by the division algorithm. X can be written as a nq plus r, where r lies between 0 to n. And now this can be written as a to the power x to the power nq, or this is a to the power x can be written as a to the power n q plus r, and this can be written as a to the power n q into a to the power r, and this can be written as a to the power n to the power q and a to the power r. And now because we have a group is a finite, so we have given a to the power n is equal to identity. So this can be written as a e to the power q and a to the power r, and then nothing but equal to a to the power r, and a to the power r is the element of a g. So we can find if x is the element of a Zn, a to the power x is equal to a to the power r, and this is the element of g. So this means we can say that a to the power x is also the element of a g. So this means phi of, we can take a to the power x is nothing but is equal to, you have a phi of a to the power r, and this is nothing but is equal to, you have a some r is there, and you have to just say that from r, the equivalence class of a r, from here you can just say that x minus r is equal to nq, and x minus r is equal to nq. This means clearly we can say that is nq. So this means n should divide x minus r. If n should divide x minus r, means we can say that x is congruent to r, and you have a mod of n, and hence equivalence class of x and the same as the equivalence class of a r. So this means this x is the element of a Zn. We can show that phi of a to the power x is nothing but is equal to x. So there is an element, we can show that image is there. So we can show that this clearly is a phi is onto. So now one more things we have left, and last one is the we have to show that this phi is a homomorphism. Now we have take a homomorphism. So we just take this. Now finally remain to show that phi is homomorphism. So we take a phi of a to the power k, a to the power m, and this can be written as a phi of a to the power k plus m, and this can be written as a same as you have a equivalence class of a k plus m. And now by the property of equivalence class, this can be written as a k addition modulo n, you have a equivalence class of a m, and now this is nothing but equal to, you have a phi of this a to the power k, and you have to just say that is the same as a plus phi of a to the power m. So there is a plus sign is missing. So we can say that here we can say that clearly this is nothing but is equal to, you can say that phi of a to the power k, and this is nothing but phi of a to the power m. So this means we can say that this phi of a to the power k plus phi of a to the power m, and that may this show that clearly phi is a group homomorphism. So we have to show that we define a map phi from cyclic group to the Zn, and then we show that this map is defined in such a way phi of a to the power x is equal to equivalence class of x, and then we have to show that this map is well defined. Also this map is a 1 1 on 2 and also preserving the homomorphism. So that means we can say that this is clearly means that G is isomorphic to Zn. So if we have to show that clearly G is isomorphic to Zn if you have a this G is a cyclic group. Now next one, if G is a cyclic group of order n, it means finite cyclic group. Now we try to prove the next part. Next part is saying that if we have a infinite cyclic group, then G is isomorphic to Z. And now let G be a cyclic group with infinite order, and support A is the generator of a G. Then we have to define a map phi of a to the power G is equal to phi of n is equal to a to the power n. So we have to take a Z to G, and then we have to this is clearly well defined. If you take a n is equal to m, then you have a n is equal to m means you have to take a phi of n is equal to phi of m, and then you can say that simply this is nothing but is equal to n is equal to a to the power m. So this is clearly we have trivially we can verify that this is map is a clearly is a well defined map. So this is phi is clearly is a well defined mapping. If n is equal to m, then a to the power n is the same as a to the power m, and then we can say that if a to the power n is the same as a to the power m, so we can say that phi of n is the same as a phi of n. So now we have to try to show that this phi is homomorphism, and this is again is a trivial. Phi of m plus n can be written as a to the power m plus n, and this can be written as a to the power m into a to the power n, and then this is nothing but is equal to phi of m n. So this is clearly is also a homomorphism. Now we have to show that this map is clearly is a 1 1. Show that phi is 1 to 1. Suppose m and n are two element in Z, but m and n are different. So we have to by contradiction we proving this m and n are the different element. We have to assuming this. So m should be greater than n, and we show that a to the power m is not equal to a to the power n. So because we have to assuming that m and different, so m should be greater than n. We have to assuming that, and then if we show that a to the power m is not equal to a to the power n, then clearly this phi is 1 to 1. So let's start. We suppose on contradiction assuming that a to the power m is equal to a to the power n, and if a to the power m is equal to a to the power n, and then you have a giving G is a cyclic group. If it is G is a cyclic group, a to the power m or a to the power n is the element of a G, and then we can write a to the power m minus n is equal to G. E is equal to same as we use a property f m a to the power inverse of n is equal to a to the power n into a to the power inverse of n, and now this is a to the power m minus n, and this is equal to identity. So this way we can write a to the power m minus n is equal to identity, where m and n because m is greater than n, so m minus n is greater than 0. So if m minus n greater than 0 means and now we have to show that any element, this is giving the identity, and this contradicts the fact A has an infinite order, because we can say this Zn is an infinite order. Clearly you know that Zn is infinite order. So this means a to the power n is equal to identity, means we have a order of A is a finite, and this is a contradicting as a infinite order. That means our assumption a to the power m is equal to a to the power n is wrong. So that means we have a clearly if a to the power m is equal to a to the power n, then m is equal to n, and this proves that this phi map is a clearly is a 1 1 mapping. So this phi is clearly is a 1 1 mapping. So now we have to put remain showed as phi is onto. Now this is very trivial. We have to pick a z belong to the G. Then z can be written as a to the power n. For some n is the element of n. Then phi of n is equal to a to the power n, and a to the power n nothing but is equal to, you have a this is z. So you can write into this z. So this phi of n is equal to, you have a z, and z is the element of a G. So this is clearly, we have to find an element of a G. We can say that z into the form. So this is clearly, we have to show that this is onto 1 1 onto homomorphism. So this means clearly we can say that this G is isomorphic to z if you have a this G is a cyclic group of a infinite order. If a cyclic group of finite order, then G is isomorphic to this set Zn. But in the case of this G is infinite cyclic group, then G is isomorphic to set of integer. And now we have a corollary from this. If order of a G is equal to prime, then clearly we can say that if G is P is a prime number, then G is because every group of a prime order is a cyclic, and if is group of order cyclic, then the since every G is a prime order, and then every group of prime order is a cyclic, so that means G is a cyclic. And if G is a cyclic, and hence the previous theorem is saying that clearly that G is isomorphic to if order of n, G is isomorphic to, you have a Zn, and then P, so you have a G is isomorphic to Z of P. Now again we can say that any two cyclic group of the same order are isomorphic. So if you take any two cyclic group of the same order, and then this is again, we can say that is also is a by this theorem we can say that it is also is a isomorphic. So if we can say that if we have a order of a, suppose we have a G is order of a G is equal to 3, then we can say that, simply say that this means is a prime order. And if it is a prime order, yes, just said that order of a G is equal to, we have a 2, then this is clearly, this G is isomorphic to Z2. And similarly we have a, or we can take a Z4 for example. If you take a Z4, means what is it? This is 2 to the power 2, and then this is a group of a prime power. So this means if we have a, if you see this, can we see this in this form? Just say that I try to this explain you. This means if we have a 2 group is a Z4, and we have a Kellen 4 group. If you see the Kellen 4 group, is these two groups are isomorphic to each other or not? So we just say that by the group table. If you take by the group table, we can into, so we have to take a Z4, and we have a K Kellen 4 group. Kellen 4 group is, you know, that is equal to, is the form of a E, A, B, C, where A square, B square, C square is equal to identity, and AB is equal to C, BC is equal to A, and so on. And then we have a Z4 is the element, you have a 0, 1, 2, 3. If you take by the this table, addition modulo 4, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Now we have a 1, 2, 3, 1 is equal to 2, then is equal to 3, 0, 2, 3, 0, 1, then you have a 0, 1 and 2, and then if you take a Kellen 4 group, you have a E, A, B, C, E, A, B, C, under multiplication, E and A, B, C, A, B, C, A square, you have a E, AB is equal to C, AC is equal to, you have a B, so this is E, and then you have a clearly write into this form E. Now we have a this is a B, B into A is equal to again C, you have a B square is equal to identity, BC is equal to A, now C into A is equal to B, then C into B is equal to C into B is equal to A, and then C square is equal to identity. So by the property of these two is isomorphic or not, we can simply say that if you take, we know that the property is phi of 0 is always mapped to identity is clearly, and now you see this from this from inverse of 1 is equal to 3, inverse of a 2 is equal to 2, and inverse of a 3 is equal to 1. Here if you see that inverse of a 1 is equal to this, inverse of a b is equal to itself, inverse of a c is equal to itself. So that means how we can construct into this form, that is the question is this. So you try, is this possible? We can show that there is a isomorphism into this, the phi of 0 is equal to E, and then you have a 2 is equal to mapping 2, you can say that phi of 2 is equal to, you have a suppose A, then if phi of 2 is equal to A, then we can say that phi of 3 is equal to, you have to check but because is a phi of 1 is a inverse of a 3, so phi of 3 is a, suppose we have a C, and then phi of 1 is equal to, we have a left only is equal to B. Now if you try to this you have in this form, that means every element that is going to image is there in this, this we have to taking is this is a composition is homomorphic preserving or not, because I just said that if we have a 0 we take a 1 and 3, so you have a 1 plus 3 is equal to, you have a phi of 0, phi of 0 is equal to 1, and now if you take a phi of 1, phi of 3, phi of 1 is equal to, you have a, and phi of 3 is equal to, you have a C, that is equal to B, then you have to just say that phi of 1 phi of 0 is equal to, you have a identity, but you have a, here you can see phi of 1 you have to define in the form of a phi of 1 is defined in the form of a, and phi of you have a 3 in the define of a C, or you take a whatever C or B, whatever you have to define in this form. So this because there is a element, you can find every element of a, here is a self inverse, but here is a elements of order of the element of this. Now here you can just see that this one of order 3, and that this group there is not any elements of order 3, so that means these two groups cannot be cyclic to each other. So that we can know, so these two are isomorphic. You can say that this is preserving is not there, we have to define in a different way. So here is a group of order 1. If you take order of a 1 is equal to, you have a 1 plus 1 plus 1 plus 1, so order of a 1 is equal to 4, but in this group there is a does not exist any element whose group order is a 4, so this means this cannot be constructed in this form. If we take a Z3, then Z3 we have to take a 3 elements into this form, and then we have to construct in the other way. We have to taking this element of a 0, 1, 2, 3 in place of a 1, minus 1, I and minus I. Then last class we have to show that these two groups are clearly is a isomorphic to each other. Okay, so now I just close with this corollary. If order of a group is equal to prime, then every group of a prime order is cyclic. If every group of a prime order is cyclic, then by this we can say that G is isomorphic to ZP. This means if we have any group of order P, prime order is isomorphic to ZP. Okay, now you remember this theorem, we have to prove that let G be a group and a normal subgroup of a G, then the mapping phi from G to the quotient group of a G by n, and define in the form of a phi x is equal to nx is a homomorphism from G on to G dash, or we can say that is a homomorphic image of pi precisely set of it. The kernel of this can be easily, you can see that kernel of is nothing but is equal to kernel of a 5 is nothing but is equal to, you can say that any element of x is the element of a G, such that phi of x is equal to identity of this G by n, and then we can say that you have x is the element of a G, such that phi of x is equal to n of x, and n of x is equal to nothing but is equal to identity in this case is a, you have a n, and if identity in this case you have a n, then this is equal to the form of this, then you have to just say that this is nothing but is equal to, you have a nx n is equal to n, this means you have a n is the element of n. So this means phi, kernel of a phi precisely the set of and this is nothing but is equal to n. So this means kernel of a set phi is nothing but equal to set, and this shows this theorem shows that each quotient group G is a homomorphic image of a G, and then we have to show that this quotient group, each quotient group of a group G is the homomorphic image of G. So now what about the naturally question comes into the mind, what can we say that is the converse of this result is true or not. The converse of this theorem is clearly this theorem, we can say that is also true. So if converse is also true, means we can suppose we are given the two groups G and G1 and homomorphism phi from G to G1, then the theorem says that kernel of a phi is a normal subgroup. We have to just say that if we have phi from to G homomorphism, and the property homomorphism is said that kernel of a phi is a homomorph, is a subgroup, and also it is a normal subgroup. So kernel of a phi is clearly is a normal subgroup of a G. Thus we consider the quotient group is the form of a because G into kernel of a phi, because kernel of phi is a normal subgroup, and that means the next theorem called is a fundamental theorem of homomorphism, and then we have to abbreviate it as a FTH, assert that the kernel of G over this quotient group is always isomorphic to the range of the group of a phi G, the range group of a phi G. So this means we can say that G1 and the G by kernel of a phi is always is a isomorphic, and this is called is the fundamental theorem of homomorphism. So we try to prove this theorem, and this theorem is simply saying that if let G and G be G1 be two groups and phi from G to G1 be a homomorphism, then we can show that G by K, where K is nothing but is equal to kernel of a phi, is homomorphism. And also if we take a composition this with the moreover if we take two more, then we have to have the phi this is or phi, then this is equal to this composition, then where eta is a natural homomorphism introduced by that the theorem previous, that this theorem we have to just say that into the natural homomorphism into this one. So by this theorem we simply say that if we have a phi from G to G1 is a group homomorphism, then we can say that there is a this composition means we have a this zeta to G by K, where define a map from G to G by K is a eta, and that eta, and then we have a clearly from G1 say this G1 G by K say, because we have to show that this is isomorphic, so we can show that a map from G by K to G1, and this is equal to we denote as a capital phi. So we can say simply is a element of X, and this is the element, all elements of this is equal to, because phi from G to G1, if you have X is the element of here, then this is the element of a phi of X, and then we can simply say that this element of a phi X is the element of X, and then the element of this is clearly know that a Kx types the quotient, because this is a quotient group and K is a normal subgroup, then this is the element of this. So now we have to proving this theorem is a fundamental theorem of this homomorphism. In the next class I provide the proof of this theorem, and now I will stop today's lecture up to this. This means we have to start in the next class by the proof of this fundamental theorem of homomorphism.